Okay, so in our last video we introduced the concept of circuits. We talked about some applications of circuits, and then we talked about concepts like electric voltage and current. And so remember, when you're talking about a circuit, you're talking about charged particles, the electrons, moving around the circuit, and basically how quickly they flow has to do with what's called current. And the thing that makes them flow has to do with what's called voltage. Now remember, voltage, the symbol for voltage is a capital V, and voltage is related to electrical potential energy. And we saw a video in the last video where we saw basically a battery, which is a very common voltage source. And the purpose of the battery in a basic circuit is basically to take those electrons and lift them up to a higher energy level. And then when they fall back down, they can use up their energy and use it to power devices plugged into the circuit. Okay, so voltage, we talked about current. Remember that the symbol for current is a capital I. Okay, voltage is measured in volts, and then current is measured in amperes. I don't know why I is the symbol for current, but it is. And so those are some of the things we talked about in the last video. We also talked about the three elements necessary for an electric circuit. Namely, you have to have some type of conducting material. You have to have a closed conducting path, because if you open up the path, like with a light switch, then the electrons cannot keep flowing in a loop. And the third element you have to have is a voltage source. And so that's how we started talking about batteries, which is a very common voltage source. Now, it turns out that there is a relationship between voltage and current, and I'm just going to keep it very basic in this video. But essentially, there is a proportional relationship where if you have more voltage, imagine if you have like a bigger battery or more volts in your battery, then that allows more current to be pushed along the circuit. And so the relationship between voltage and current has a name, and that is called Ohm's law. Okay, and Ohm's law is an equation, and the equation for Ohm's law looks like this: V equals I times R. Okay, now V we know is voltage, that's measured in volts. I we know is current, that's measured in amperes, but R is something new, and R is what's called resistance. And again, we're just going to keep it very, very basic in this video. We could go into a lot more detail, but I don't want to complicate things. And so this is called Ohm's law, V equals IR. It's an equation that relates these three concepts. Now, we talked about voltage before, and we talked about current being, how quickly those electrons are moving around the circuit, but R is something new. Like I said before, R is a symbol for resistance, and basically what resistance is a number that measures how easy or difficult it is for current to flow in a circuit. And so the more resistance you have, the harder it is for those electrons to flow, generally speaking. Okay, and so this is called Ohm's law, and we're just going to do some very, very basic calculation with Ohm's law. Pause it here if you need to write any of this down. I'm going to erase it. Okay. And here's just some general facts about resistance. Okay, number one, the unit for resistance is the ohm. Okay, it's named after a guy, that was his name, Ohm. And the symbol, I don't know why, is a Greek letter. It looks kind of like a horseshoe. Here it is right here. Okay, that is the symbol for resistance. And that is an uppercase omega. Okay, and so you have capital R for resistance. The unit is the ohm. And the way you write an ohm is with this horseshoe symbol, this capital omega. So for example, if I had, a device that had a resistance of 10 ohms, okay, I would write R equals 10, and then this little symbol right here represents ohms. That is the unit for resistance. And again, what that means is it's basically a number that tells you how easy or difficult it is for current to flow through a device. Okay, so if you imagine attaching, let's say, a 9-volt battery to two different devices, and one of them has more current flowing, the one that has more current flowing has a higher or has a lower resistance. Okay, higher the resistance, the more difficult it is for current to flow. Okay, so if you look at this graph, for example, you can see, let's say we have I don't know, 9 volts right here. And for 9 volts, we get way more current on a low resistance device than we do with a high resistance device. Okay, and so again, resistance is basically a measure of how easy or difficult it is for current to flow through a device. For a higher resistance, it takes more voltage to force the same amount of current to flow. And this little picture right here is just a cute little analogy. Remember, voltage is basically what's making the electrons move to begin with. It's what's pushing the electrons around because it has to do with their electric potential energy, lifting them up to a higher energy so they can be deposited to a lower energy later on. The current is what is actually flowing, right? Those electrons flowing through the circuit, and resistance, this little ohms right here, is basically what makes it difficult for current to flow. Okay, so that little picture right there is a cute little analogy showing you the concept of electric resistance. Okay, so pause it here if you need to look at that. Okay, and so we're just going to do some very basic examples with Ohm's law. Okay, so here's example 1. It says the voltage across the light bulb is 1.2 volts. Okay, so here's my light bulb voltage. Remember, V is the symbol for voltage, but it's also the symbol used for the unit. Okay, so I could write V equals 1.2 V, and this V represents voltage, and this V over here represents volts, which is the unit of voltage. It's kind of confusing. It's basically the only place in physics where the symbol and the unit have the same letter, which is a capital V. I know it's kind of confusing. Okay, so 1.2 volts is the voltage across this light bulb. The current that flows through the light bulb, okay, remember current is a capital I, is 0.02 A. Remember that capital A represents ampere or amps. That is the unit for current. That is a capital I. And we're asked to calculate the resistance of the light bulb. Now, by the way, this problem is not necessarily super realistic. 1.2 volts is not a lot of voltage. Typically, if you have like a battery powered light bulb, the voltage on a like AA battery is like 1.5 volts. You can also buy, 9 volt batteries at the store. If you plug something into like your outlet in your house, that's probably like 120 volts. Okay, and so this is not necessarily a realistic example, but just to show you how to use Ohm's law in a calculation. So Ohm's law, V equals IR. Ohm's law is our equation that we're going to use. The voltage is 1.2, so I'm just going to plug in here. The current is 0.02, that's my I put parentheses there, and if I want to solve for R, I need to divide both sides by 0.02, like so. Okay, and if you type that into the calculator, then you will get the resistance. And just a quick reminder, remember that the unit for resistance is the ohm, and the way that you represent that is with the horseshoe looking symbol that is an omega. Okay, so R equals 60 ohms is how you would say that. Okay, actually let me try to do a better job on that ohm. 60 ohms, something like that. Okay, so very basic type of calculation. And you might ask, what is the purpose of resistance? Do we want like high resistance or low resistance? And it depends on the situation. In some situations you want high resistance, and some situations you want low resistance, depending on, what it is you're trying to do with your circuit. In the light bulb, if the resistance is too high, that can cause a lot of heat to be generated, which might be bad. On the other side of that is, if you have a higher resistance, that also leads to a lower current, and if you have a lower current, that device might be safer too, because current is actually what can harm you or damage you. You can be electrocuted if the current is too high. If you've ever, tested out a 9 volt battery by placing it on your tongue, you can feel a little zap when you do that, but that current is so small that it's not dangerous to you. Whereas if you were to stick your finger in an outlet, please don't do that, the current through you might be enough to hurt or kill you. And so current is actually what's dangerous in a circuit. Okay, and so, depending on the situation, you might want a high current or you might want a low current. Okay, so pause it here if you need to look at this example. Okay, just to do one more quick example with Ohm's law, we have a 9 volt battery. Okay, so I'm just going to identify my givens. 9 volts, that is the voltage of my battery. Remember, a battery is a very common voltage source. And I have a resistor that is 50 ohms. So here's my R. Now, if you don't know what a resistor is, you can buy resistors at any electronics store. They're used to build very simple circuits. Any device has some intrinsic resistance in it. If you just try to attach a voltage source to it and measure the current, then it has some resistance. But you can actually buy specially designed objects that are called resistors that have a set constant resistance. Okay, and so that's what it means by resistor. And so again, you can buy those at any electronic store if you want to make your own basic circuit. That's what a resistor is. And we're asked to calculate the current that flows through this resistor. So we have Ohm's law, V equals IR. I have identified my givens. I plug those in. 9 volts. Okay, I'm looking for I, that's my current. R, the resistance, is 50 ohms. That's given right here. Okay, so there's my 50. And so I is going to be 9 divided by 50, which is going to be 0.18. Remember, the unit for current is A, that is ampere, okay, or amps as some people say, 0.18 ampere. Okay, so 2 basic calculations involving Ohm's law. So please pause it there if you need to take a look at that. Okay, now I'm going to erase this really quickly. Okay, by the way, in case you're wondering, is that a lot of current? Is that a little current? That's not a ton of current. It is maybe enough to hurt you. Just to give you an idea, most modern houses are designed with their electrical circuitry to work with up to 100 or 200 amperes. And so this is not, a super high current. But some devices that you might plug into your house outlets use more current than others. For example, power tools use a lot of current. Your electric dryer, both a hair dryer and clothing dryer, require a higher current. And so even though this number is relatively small, especially compared to what you can get from your outlets at home, it still might be dangerous to you. Okay, so just to put that number into context. Okay, so the last thing we're going to talk about in this video is factors that affect resistance. Okay, and so we're talking about this in the context of electrical wires. Now you might have seen lots of different electrical wires before. Some of them are really thin. For example, like your if you ever look at your headphone wires, those are really thin. Some wires are really thick. For example, if you look at your computer and where it's plugged into the wall to charge, it's probably a much thicker wire. And the thickness is one of the factors that affects the resistance of the wire. Okay, and so the wire itself, that's typically made of copper or maybe aluminum, has some amount of resistance. And there's 2 factors that affect the resistance of the wire. Well, there's actually 3. The third factor, which we're not going to talk about, is basically the material that the wire is made of. But in this class, we only worry about 2 of those factors, and that is the length of the wire and what's called the cross-sectional area of the wire. And that's basically a fancy way of talking about the thickness of the wire. Okay, and so here's what you need to know about the factors that affect the resistance. Again, we're talking about of a wire. Okay, just for the sake of conversation. Here's what you need to know. The longer the wire, the higher the resistance of the wire is. And the reason for that is very simple to understand. Remember, resistance basically measures how easy it is for electrons to flow around in a circuit. And so if you think of the water analogy, when we talked about the water analogy, the current was like the water flowing through the pipe. Well, if you imagine a longer pipe, it's more difficult for the water to flow because it has farther to travel. Okay, so if you carry over this analogy to electricity, the longer the wire is, the higher the resistance. Now, the other factor that affects resistance of a wire is what's called the cross-sectional area, or you might just call that the thickness of the wire. Okay, the thicker the wire, the lower the resistance is. And the reason for that is also kind of intuitive. Again, if you think of water flowing through a pipe, it's easier for water to flow through a pipe if the pipe is wider around if the pipe is thicker, because that means there's more space for the water to travel in. Okay, and it's the same thing for an electrical wire. And so wires that are thicker, for example, this wire right here on the far right is thicker compared to this tiny wire over here, and so this would have less resistance just because it's a bigger wire. Okay, so again, if you think of the water analogy, those two factors that affect resistance of a wire are kind of intuitive. And the third factor that we're not really going to talk about is the material that the wire is made of course, also plays a role in the resistance of the wire. Some materials have naturally high resistance, for example, like plastic or rubber. Don't have or have a very, very high resistance. They're called insulators. And then some materials like copper or aluminum or metals in general tend to have a very low resistance. And so that's the third factor that affects resistance. We're not going to really talk about that. Mainly you just need to know about the length and the cross-sectional area affecting the resistance of the wire. Okay, so we're just going to look at two quick simple examples with that, and then we'll talk about power in the next video. Okay, so two really quick examples. Here is example 3, and it says the two pieces of metal shown are made out of the same material and they have the same length. Which of these do you think will have the greatest resistance? Now remember, the three factors that affect electrical resistance of a wire are the material, which in this case they're made out of the same material, the length, in this case they have the same length, and the cross-sectional area or the thickness. Okay, now looking at these two, they're made of the same material and the same length, but A is thicker. Okay, that means A, because it has a greater cross-sectional area, that means it's thicker, that means it's going to have less resistance. So the answer to the question, which will have the greatest resistance, has got to be B. Okay, the piece of metal B. Okay, because it's thinner, it's going to be more difficult for those electrons to travel through, and therefore it's going to have a higher resistance. Okay, so just a really simple example with that. Pause it there if you need to look at that. And then just one more really quick problem. Here's a problem that says all the following wires are made of the same material but are different sizes. Identify the wire with the lowest resistance. Now, if they're made of the same material, that takes away one of those factors that could affect resistance, and the other factors being length and area. Okay. So if we want the lowest resistance, okay, that means we want it to be easiest for the electrons to travel through. That means we want to have a big area, and we want to have a low length in order to have the lowest resistance. And so which of these pipes is going to have the biggest area and the lowest length? Well, the biggest area that I see, this one has an area of A, this has an area of 2A, 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 and A. Okay, so we can eliminate this answer choice and this answer choice because those are not the thickest possible wires. Now, these three, answer choice B, C, and D, all have the same cross-sectional area, and so we want the one that is the shortest because that's going to have the least amount of resistance. Okay, and so the one that's shortest is going to be B. Okay, so in this video we talked about Ohm's law, we talked about electrical resistance, the factors that affect the resistance of a wire, and then we did some simple examples with both Ohm's law and with factors that affect resistance of a wire. Please let me know if you have any questions. Again, we're just keeping it very simple and basic. I just want you to be familiar with these terms in case you encounter them on your day-to-day life, because circuits are all around us, like I said, and so it's good to know some of these basic facts and information. As always, please let me know if you have any questions, and I will see you in the next video.